we're going to give a very creative proof that the square root of 2 plus the square root of 3 plus the square root of 5 is an irrational number. That means that it cannot be expressed as a ratio of two integers, so we cannot write square root 2 plus square root 3 plus square root 5. We cannot write it down as p over q, where p and q are integers and q is not equal to 0. We cannot find a pair of integers, and this looks like a difficult proof because if you think about it, we have to show there is no pair of integers p and q. You have to show nothing is possible that expresses root 2 plus root 3 plus root 5 as such a ratio. So how are we going to approach this? So I assume that you kind of sort of familiar, have seen before the proof that the square root of 2 is an irrational number, but even if you haven't, don't worry, we'll actually go through a similar argument eventually. But the basic idea is we need to understand this number, right? And we need to rigorously prove it's irrational. So how do we understand this number? We don't know root 2, root 3, and root 5. You know, if you try to write out, they have infinite decimal expansions, you cannot write them out. What we do know about them, the fundamental property, is that root 2 squared is 2, root 3 squared is 3, and root 5 squared is 5. That's the property we're going to have to use. And so we're going to have to manipulate this equation. Okay, so first of all, I'm not going to think of the p over q. I'm just going to call it x. Okay, so I'm just going to write x is equal to square root 2 plus square root 3 plus the square root of 5. And I'm going to show you something. You know, you may wonder why I did this approach rather than the other one. So I'm going to show you the failed approach first as an instructive sort of methodology. But what happens here is that we can square x. We can square both sides, right? Because we want to get rid of the square root. Somehow this expression has 3 square roots. We want to get rid of the square roots. But what happens if we do that is if we square x, we run into an issue. The issue we run into is that you still get 3 square roots when you square x. Because what happens when you look at root 2 plus root 3 plus root 5, what happens is if you square it, you're going to get, basically use the binomial theorem. So you're going to square each of these terms. So you're going to get 2 plus 3 plus 5, that's fine, plus 2 times square root 2 square root 3. Square root 2 square root 3 is square root 6. So 2 times square root 6 plus 2 times square root 2 square root 5, which is square root 10. So 2 times square root 10 plus 2 times square root 3 square root 5, which is 2 times square root 15. Now, as you can see that after doing that square, we still have 3 square roots. We haven't simplified our problem. Somehow, we want to simplify x by squaring it, so that's not working. So what we instead do, and this is again showing you how math works, you know, it's not always the most polished method. What we want to do instead is you want to actually subtract root 2 from both sides and write x minus root 2. X is the thing we want to show is an irrational number. Okay, so we look at x minus root 2, and that's going to equal to the square root of 3 plus the square root of 5. And then what we do is we square both sides. Okay, and by the way, if you're enjoying the content so far and the approach I'm using, don't forget to smash that like button and use the hype feature. You're clicking the hype button. The video is within 7 days old. It helps disseminate the video and recommend it to as many different people as possible. It really helps small channels to grow. So we square both sides and we've got this. And now at this point, you know, we're going to do a proof by contradiction. Okay, so we're going to start off with, I'm going to say that assume that x is a rational number. Okay, assume for a contradiction that x is a rational number and will lead to an absurd conclusion. Now, if we've got this equation, we square both sides, the first thing we're going to observe is that we're going to simplify the number of square roots. Instead of having 3 square roots in the equation like we had here when we squared x, we're going to have 2. And how that's going to work is the following. We got x squared minus 2x square root 2 plus square root 2 squared, which is 2, is equal to the square root of 3 plus the square root of 5 squared. What happens there? Well, you get square the square root of 3, square the square root of 5, and plus 2 times square root 3 square root 5, which is 2 times square root 15. And observe that in this equation, we only have 2 square roots in this equation. Okay, we have this square root and this square root, versus this equation, we've got 3 square root terms. So now what we want to do is just bring all the square root terms to one side of the equation, assuming our contradiction, our hypothesis that x was a rational number to get a contradiction. Okay, so let's do it on that side of the board. All right, so now let's go for it. So let's like put all our square root terms on the right side of the equation. So we've got x squared, you know, you've got 3 plus 5 is 8, 2 minus 8 is minus 6. So you subtract 8 from both sides, we get x squared minus 6 is equal to 2x square root 2 plus 2 times square root 15. And by the way, we could have, you know, subtracted square root 3 from both sides in the beginning and got x minus square root 3 squared is square root 2 plus square root 5 squared. That would have also led to a, you know, similar approach, okay? But we've got this far, and now observe the following. We assumed for a contradiction x was a rational number, x being square root 2 plus square root 3 plus square root 5, right? So this was our x in our proof. And we just labeled it x to keep things convenient. And now that means that therefore, of course, x squared minus 6 is a rational number. The square a rational number, add rational numbers, multiply rational numbers, they're all rational numbers. Okay, so that's fine. So now we know that 2x square root 2 plus 2 square root 15 has to be a rational number. Okay, so we're deducing more and more and more from this initial hypothesis that x is a rational number. And we're going to get a contradiction eventually. So we've got that far. So now we know that therefore, I'm going to write it out, therefore 2 times x square root 2 plus square root 15, okay, and I'm going to factor out a 2, this is a rational number, okay? So of course, if this is a rational number, that implies that therefore, so this is a rational number, I'm going to put this symbol. This means Q is the set of all rational numbers. This means it's an element of Q. It's a rational number. Just another way of saying it's rational. Now, therefore, that means you divide by 2 a rational number, you get a rational number again. So therefore, what we do is we get x square root 2 plus square root 15 is also a rational number. And now we're getting somewhere. Now we're going to again square both sides. Remember, when you square both sides here, what happened is we got rid of one square root. Instead of having 2 square root terms that we added together, we just have one square root term. We want to reduce the number of square root terms. Okay, it's going to be easy to deal with one square root term. So therefore, we square both sides. We get x square root 2 plus the square root of 15 squared is also a rational number, which implies that, squaring both sides again, use the binomial theorem. So we get 2x squared plus 15. So I'm squaring both terms plus 2 times. So 2 times x times square root 2 square root 15 is square root 30. And that is going to be a rational number. Now, if you subtract rational numbers from rational numbers, you're still rational. Remember our initial hypothesis? X was assumed to be a rational number. Therefore, 2x squared plus 15 is also a rational number. Therefore, you subtract that, you're going to get from this rational number, you're going to get the remaining term, which is just this single term, 2x square root 30 is rational. And again, because 2x square root 30 is rational, that implies dividing by rational numbers is still rational. You just proving this, you have p over q, p prime over q prime, you take the ratio, it's still a ratio of two rational numbers. You can verify that. So therefore, 2x square root 30 is a rational number. Therefore, that means that square root 30 is also a rational number. And that's our conclusion from our initial hypothesis that x was rational. We're getting square root 30, which is actually the product of the square roots, is also rational. And now we're almost done. Now we have to get a contradiction from this. Let's do that. And a huge thank you so much to Alex and Stephan for ongoing Ruby support on Patreon, and Nathan for ongoing Gold support on Patreon. Makes a world of difference to the channel. And I also am deeply grateful to the YouTube channel members Aman, Rob, Shabeed, Nicolas, and Stephan for their ongoing support as YouTube channel members. Thank you so much to everyone who supports the channel. Every dollar, every small contribution makes a world of difference. I run the entire channel on my own, and all the contributions really help me free up time to produce and continue producing infinite free accessible math education, giving you a unique perspective as a professional mathematician on YouTube. So thanks so much. And there are also exclusive perks that come with support that you can check out, either clicking the join button on YouTube or checking out Patreon, links in the description. So let's now get into the proof. Finalizing, we've got to root 30 is a rational number. Now we're going to do a proof by contradiction, continuing our current proof. We're going to assume that, we know that root 30 is irrational, therefore it's equal to p over q, where p and q are integers. Okay, so p and q are integers, and we're going to assume that's in lowest terms. Okay, so this is going to be very similar to the proof that root 2 is irrational, if you've seen that proof. We're going to assume it's in lowest terms. That means you can't cancel something from both p and q. It's not 3 over 6, which is just half. Okay, we reduce it down to half in that case. We write it in that form. Now root 30, we don't like square roots. We've been trying to get rid of them this entire video. Let's now do one more time. Let's square both sides. So we're now going to get that 30 is equal to p squared over q squared. And of course, multiplying both sides of the equation by q squared, that means 30q squared is equal to p squared. Okay, now I'm going to show you now that implies that actually it was not the case that p over q was in lowest terms. You can cancel something off from top and bottom. So let's do that. All right, so 30q squared is p squared. Now, this is going to be very similar to the proof that, root 2 is irrational. Basically, we know that 30 is even. So 30q squared is p squared implies, therefore p squared is even. But the square of an odd number is always odd. So p squared is even means that p had to have been even. P had to have been an even number. Okay, so therefore p is even. But if p is even, therefore p squared is divisible by 4. P squared is divisible by 4, but p squared is 30q squared, and 30 is not divisible by 4. 30 is only divisible by 2. Okay, so 30 is equal to like 2 times 3 times 5, right? So it's not divisible by 4, but it's divisible by 2. Therefore, if p squared is divisible by 4, that means q squared has to also be even. Q squared has to be divisible by 2, so therefore q squared is even. Same reasoning therefore implies that q is even, but if q is even, p is even, we did the same reasoning, q is even, p is even, that means this fraction wasn't in lowest terms. So that is a contradiction, therefore root 30 is an irrational number. And another way of thinking about the argument, if you're thinking about this lowest terms thing, this contradiction aspect, you can also just say sort of like, whatever it is, this argument shows we can cancel a 2 from it. But you can't keep canceling a 2 from top and bottom. Eventually you're going to reduce down to a fraction where you can't do that anymore. And then the argument shows that's a contradiction. Okay, another way of looking at it. But anyway, that shows root 3 is irrational, and that's a contradiction because we said it was rational assuming x was rational. So therefore x is an irrational number. Now I've got 2 fun videos for you. If you enjoyed this video, I've got a challenge for you. Can you find a polynomial with integer coefficients that has root 2 plus root 3 plus root 5 as a root of that polynomial? Can you actually find it? We sort of, before I erased it, we sort of were heading in that direction. And if you want a pointer and you want to understand the process for that, a really fun video, it's just 3 minutes. Check out this video, it's going to pop up on the screen here. It basically finds a polynomial that has root 2 plus root 3 as a root. It's a degree 4 polynomial, it's very fun. Check that video out, you're going to love it. And another fun video you're going to love is the famous number e. And there's a really fun, elegant, creative, intuitive proof that it's irrational. Check it out, you're going to love it. It's a very popular video on my channel. Hope you have an amazing day.